All right, in this little video, we're going to kind of continue this idea of solving radical equations, but we're going to move it along in a little bit more difficult area. All right, here we go. Same 5. Nothing has changed that way. So we take a look at our first equation here, that square root of 7w minus 12 is equal to w plus 2. We've isolated one of the radicals, and now we look to the index to see what we should raise both sides to, and this happens to be a 2. And so we'll go ahead and we'll raise that to the power of 2. Whoop. The power of 2. So we're going to square that left side. We're going to square this right side and be very, very careful of this right side. As some students will attest to, this could be a problem. So if we square the root, they cancel each other, and now we're left with 7w minus 12 is equal to. And now we have this thing squared, which is actually w squared plus 4w plus 4. 34 letter F word it. And no, as my students will probably be watching these videos, I have a rule of 3. If you can get me to say a dirty 4 letter F word 3 times in the same semester, I buy a pizza party. I'm not doing it because I've already had twice, the other twice. So anyway, there's probably other videos about the dirty 4 letter F word, so I'm gonna let that be. All right, go ahead and clean up by combining like terms. You'll notice it really doesn't matter whether or not we have to do that because there are no radicals left. So we can go ahead and skip right to the method of solution. So we're going to go ahead and add 12 to both sides. I'm going to subtract 7w as well. That's going to move everything over to this right-hand side, leaving me with 0. So I have 0 is equal to w squared minus 3w plus 16. And then to factor this, my students know the only way to solve this is to factor. If you happen to know the quadratic formula, I recommend using it here. But we're asking, are there any numbers that will go in here, and real numbers are the only ones that we're selecting. Well, 2 numbers that multiply to 16 that add to 3. Not happening. Not happening. So as it stands right now, this has no solution. At least not in rationals. And so if you would prefer it and you wanted me to do this out, I can. If you want to go ahead and just kind of skip ahead past this part, you're more than welcome to. I'm going to switch off colors here to go ahead and do this. If you're familiar with it, you can use the quadratic formula. The quadratic formula says x, which in this case is a variable, or whatever variables you're using, is negative b plus or minus the square root of b squared minus 4ac all over 2a. And if we identify our pieces, a is equal to 1, b is equal to negative 3, and c is equal to 16. We can go ahead and plug this in. So w is our variable. This is equal to 3 plus or minus the square root of, and then we have, let's see, b squared, so that'd be 9 minus 4ac minus 4 times, that's 64. As you can see, this is already going to be an issue because we're going to have imaginary numbers. And so this is going to be minus 64 be 55. Ugh, yuck. So after this, plus or minus the square root of negative 55 all over 2, that's going to give you 3 plus or minus I roots of 55 all over 2. So those are your 2 answers, 3 plus I root of 55 over 2 and 3 minus I roots of 55 over 2. My class really doesn't care. Okay, so we're going to head and move on to this next one. As far as we are sitting where we are, it's no solution. So now we go ahead and move on to the next one, and we do have to actually go up and use that very, very first thing. And so we isolate one of the radicals. It does not matter which one, just as long as you isolate one of them. So I'm going to go ahead and I'm going to add root of 3x plus 5 to both sides. Root of 3x plus 5. And that leaves me with the square root of x plus 2 is equal to 3 plus square root of 3x plus 5. Now, go ahead and raise both sides to the square. And when I say this, I mean both sides, the entire right side. This radical cancels that square, leaving me with x plus 2. This other side you have to be extremely careful on. Just like we were over here with our w plus 2, this is going to work very much the same way. The trick here, it's not really a trick, it's just a, if you happen to know it. But if you have x plus or minus a, it doesn't matter which this is, but it's x squared plus or minus, this keeps the same sign as whatever's in here, 2ax plus a squared. So the idea here is you're going to square the first, you're going to square the last, it's always positive on both. You're going to multiply the stuff in the middle to include the sign, and you're going to double it. That's the middle term. So in keeping with that, I'm going to go ahead and complete this out here. I'm going to square the first. I'm squaring the second. The square and the root cancel, leaving me with just 3x plus 5. Always put that in parentheses. Always. And then we're going to multiply these two things inside, 3 times the root, and double it's 4 plus 6 times the root of 3x plus 5. That's it. You notice I put the 2 squares up front? There's sort of a reason for that. Okay, so now we raise both sides. Now clean up by combining like terms. Here is where we're going to have to use this cleaning up part. So now I have 9 plus 3x plus 5 gives me 3x plus 14 plus 6 roots of 3x plus 5, and that is equal to x plus 2. I'm going to go ahead and I'm going to move all of this x stuff, anything that is not part of the radical term, I'm going to move over to the other side, thereby going back to step 1 and isolating the radical. So I'm going to subtract 3x and subtract 14 from both sides. Subtract 3x minus 14. That's going to give me negative 2x minus 12 is equal to 6 square roots of 3x plus 5. Okay, so now I know I said before you should isolate the radical. I fudged my own rule just a little bit. So when we get to this part, we can actually utilize one of our rules for exponents and radicals. And that is, if I raise two things that are being multiplied to a power, then I can distribute the power amongst them. So when I square both sides, I can actually square the 6 and the square root at the same time. So I'll eliminate the root with the square. On this other side, I've got to square it. I'm going to kind of help myself out here, to tell you God's honest truth. I am going to factor out a negative 2, x plus 6 is equal to 6 roots of 3x plus 5. And then I'm going to square both sides. Now, the reason I'm doing this is more for my sanity than it is yours. I can see the rules that I have to use. And the rule I have to use, by the way, is a rule that looks very much like this. It's if you have two things and you raise them to an exponent, then you can distribute the exponent among them. And if you need a little quick proof of that, let me know in the comments below, and I'll try to provide one real quick. All right, so I'm going to square both sides here. And when I do that, I'm going to square this piece here for 4. And then I'm going to square the stuff inside here. And that goes as such. X squared plus 12x plus 36 equals 36. And then times the square of the square root just gives us this stuff inside. Okay. So now that I've fully completed that, I'm going to go ahead and clean that up just a little bit. I'm going to start by dividing both sides by 4. This affects only the 4 and the 36, or at least that's the way I'm going to make it affect it, because those are both have factors of 4. That's going to leave me with x squared plus 12x plus 36 equals 9 times the quantity 3x plus 5. And all I'm going to do is I'm going to clean this up a little bit. X squared plus 12x plus 36 is equal to 27x plus 45. From here, I'm going to go ahead and solve. Now, since I already have an x squared, since I have this x squared term over here, I'm going to move everything over to that left-hand side and make this 0. So subtract 27x and subtract 45 from both sides. That's going to give me x squared, and this is minus 15x minus 9 is equal to 0. 2 factors of 9 that subtract to be 15. It doesn't happen. So this is not factorable. So again, we're going to have no solution. Okay, again, if you happen to have the power of the quadratic formula, this does have a solution in radicals, but not in rationals. So that you're going to have 2 irrational solutions in this, and they will be conjugates of one another. But we're going to stop there on that one. You can kind of duplicate what I have over here in blue. Okay, so we're going to finish up with this little guy here. And again, it's very much the same thing, only this time we are going to get a solution. It just might not be easy to find right away. So we're going to start by isolating one of the variables. I'm just going to subtract off 3x minus 5. So that root gets subtracted from both sides. That's going to give me the square root of 2x plus 10 is equal to 6 minus the square root of 3x minus 5. And then I'm going to go ahead and raise both sides to the square because that's going to eliminate that radical on the left. So that's going to give me 2x plus 10 is equal to, and again, our little trick from before, square the front, square the back, and it's always positive. Multiply the 2 things inside, so negative 6, and then double it for negative 12 roots of 3x minus 5. Clean everything up. So if we combine like terms, we get 2x plus 10 is equal to 36 minus 5 is 31 plus 3x minus 12 roots of 3x plus minus 5. And then I'm just going to pull everything over to the other side. So again, since I have a radical term left, I'm going to go ahead and isolate that. So I'm going to subtract 31 and subtract 3x from both sides. And I get negative x minus 21 is equal to negative 12 roots of 3x minus 5. For grins. It's not necessary, but for grins. I'm going to go ahead and I'm going to multiply both sides by negative 1. And the reason for this is I just don't like the negatives, and I can take care of all of the negatives if I just multiply both sides by negative 1. Especially on this left-hand side to deal with negatives, it's just not all that easy. So if I do that, I get x plus 21. The negative 1 times the 12 times the negative 12 gives us positive 12 roots of 3x minus 5. Now we go through the method. So here we're going to go ahead and we're going to raise both sides to the square. If you don't happen to know these numbers off the top of your head, don't worry. You'll have to calculate them. It's no big deal. Square the front to get the front. Square the back to get the back. 21 squared is 441. Multiply the 2 things inside, so 21x, and then double it for 42x. Equals square 12 for 144 times, and then you're going to square the root, which eliminates the root for 3x minus 5. Now normally, and my students already know this, but normally what I would do here is I'd probably try to divide by 144 just to make numbers smaller. But if you look at the leading coefficient over on the left side, it's 1. I'll be having a lot of fractions, so I'm not going to do that this time. What I am going to do, though, is I am going to clean this up just a little bit, giving us x squared plus 42x plus 441 equals, and I'm going to go ahead and distribute this through. 3 times 144 is 432x minus, and this is 720. So now I'm going to go ahead and I'm going to solve. So I have an x squared term, and so that means I'm going to go on everything over to that side since it's already positive. I'm going to subtract 432x and add 720 to both sides. Subtract 432x and add 720. And then I have x squared. If I subtract these two, I get minus 390x and then plus 1161 equals 0. It's gross. I'm not going to lie, it's gross. So if you struggle with this, it's a toughie. But what we can do to kind of help ourselves out is, well, if we got to add these two things to get 390. So if I add 1 and 1161, which are the two factors, or two of the factors, I get 1162, which is not that. So now I can notice this is not even, so I don't have to check any even number. It won't work. So the next thing I try is 3. I can add the digits of this number to see if it's divisible by 3. And I have 1 plus 1 is 2, plus 6 is 8, plus 1 is 9. Not only is this number divisible by 3, but also 9. So I'm going to try 3 first. If I divide 1200 by 3, I get something close to 400, which is close to this. So this, in fact, 1161 breaks down into 3 and 387. And if I add them, then I do get 390. So this is going to break down into x minus 3 and x minus 387 is equal to 0. Setting both equal to 0, it's x minus 3 equals 0 or x minus 387 equals 0. Finally, just cleaning this up, x is equal to 3 or x is equal to 387. Again, we got to go back to that whole, did we get an answer? Well, it looks ugly. It looks ugly, but we could have. We got two possibilities. We got to check each one. So 3 and 387 is what we got to bring right back to the very beginning. So I'm going to take this over here and I'm going to check it. This time with 3 up here, up top, and with 387 on the bottom. So I get the square root of 2 times 3 plus 10 plus the square root of 3 times 3 minus 5. Is that equal to 6? Well, this is the square root of 16. This is the square root of 9 minus 5 is 4, which is 4 plus 2, and that does in fact equal 6. So 3 checks out. It's okay. So now we try 387. The square root of 2 times 387 plus 10 plus the square root of 3 times 387 minus 5, is that equal to 6? Well, remember we're adding them. So if one's bigger than 6, we can stop. Well, 2 times 387, even if I just said 600, is like, this is 300. This would be 600 plus 10. That'd be 610, and the square root of 610. Yeesh. Well, that's going to be somewhere, right around 25. I'm already too big. This is no way. No, this doesn't work. And you can do it out if you want. 3 times 387. Oh, or I'm sorry, 2 times, that'd be 780. And so we got to subtract off 6. And so that would be 774. 784. So it'd be the square root of 784 plus, and then the square root, oof. Wow. Well, let's see. That's 1161 minus 5 is 1156. I have no idea what the square roots of those are right off the top of my head, but I can tell you what, they're not going to add to be together to 6. But if you want to go ahead and figure it out, go right ahead. So out of all of that stuff, our only acceptable answer is 3. The method that you use to solve these things can sometimes introduce what they call extraneous roots or extraneous solutions. These are solutions that are kind of introduced by the method of solution that you choose to use for this particular problem. Sometimes there's no way to get around it. Other times different methods would produce different results and then constrain all of your possible solutions down to what's actually allowed. Because of these methods, it's a nice easy method to follow. We have to go back and check to make sure that we're not introducing a falsehood at the same time. That's it. You do it all the exact same way. Thanks for watching.